Hello, everybody. Let's start talking about section 9.1 here. This chapter is about systems of equations, and we're going to begin with systems that have two variables. So basically, what a system of equations is, it's going to be multiple equations with multiple variables. And the big idea is that the number of equations and the number of variables needs to be the same. So you could have two equations with two variables, three equations with three variables, four equations with four variables, etc. The most basic type is two variable systems. And if you've got a pair of equations with X and Y in them, one way you could go about finding their solution would be to graph them, because I'm sure you've had experience graphing equations of lines in the past. If you were to graph the first equation they give you, and then if you were to graph the second equation they would give you, one of three things would end up happening. The most common result would be this one right here, the first one, where you would have what's called an independent system. So you'd have a pair of lines, you've got a red line and a blue line. Somewhere there's a point where they cross, and the coordinates of that point would be the solution to the systems of equations. That is known as an independent system because the solution is a single point independent of everything else. The next possibility is you could have what's called an inconsistent system. An inconsistent system is going to happen when you have a pair of parallel lines. So, fun fact about a system of equations is that the point of intersection is the solution. If there is no point of intersection, there is no solution. That's called an inconsistent system, which happens when the lines are parallel and they will never meet. The last possibility you could have is what's called a dependent system. And basically, through some quirk, it turns out that the two equations you have end up describing the exact same line. So if you were to graph the first equation, and then if you were to graph the other equation, they would basically line up right on top of each other, and you wouldn't be able to tell the difference between them. And it would just look like one line because the two equations of the lines describe the same thing. And so that would mean that there are infinitely many solutions. There's a countless number of points on this single line where they would overlap, because every point on that line is a point of intersection. It's called dependent because the idea is, depending on if you're on that line in the first place, it will be a solution. There are lots of other points out there that are not solutions, that are not on the line. So depending on if it's on the line in the first place, that would be a solution to the system. And that's called a dependent system. And it's a weird quirk where the two equations happen to describe exactly the same line. So the first thing that you could do with a system is just check and see if the coordinate that they give you is in fact a solution to that system. So here they say, determine whether the ordered pair 5, 1 is a solution to the given system of equations. And they got the systems there for you. You got the first equation, x plus 3y equals 8. The other one is 2x minus 9 equals y. And the trick here, it must be true for both equations. That's the catch. One is not good enough. If you plug in the X and Y values for both equations, it must be true. So if they give you the 0.51, that basically means the X value is 5 and the Y value is 1. So if we put this in the first equation, X plus 3Y is equal to 8. Change the X to a 5. Change the Y to a 1. Work out what that is. 3 times 1 is the number 3. 5 plus 3 is indeed 8. So 8 equals 8, and that is true. That checks out. That is equal to what it is supposed to equal. Next, we're going to take the other equation, 2x minus 9. That should equal y. Okay, so the X value again is a 5. So we're going to replace X with 5. The Y is a 1. We're going to replace Y with 1. Two times 5 is 10. 10 minus 9 is 1. So you end up with 1 equals 1. And lo and behold, that is also a true statement. So both equations work. Both of them check out. It is true both times. So the answer to the question is yes, it is a solution. And so that's what it means for a point to be a solution to a system of equations. If you were to plug in the X and Y values in both equations, it will give you a true statement. You will see the picture there of both of those equations of lines. If you were to make a graph of each of those equations, you would have a blue line and a red line as shown. And you can see there the point of intersection, which is 5, 1, which is visually showing us that 5, 1 is a solution. Because in concrete terms, that's what a solution to a system is. It is a point of intersection of two lines. So there's a bunch of different ways to go about solving systems of equations. The first method is to use substitution. What you do with substitution is you pick one of the equations. Usually you want to find a variable that's all by itself with no number attached and no negative attached. Solve for that variable, take the result you get and plug it into the other equation. And then after you do that, solve for the first variable, go back and plug in your result and find the second variable. So for this one, they give me this example, negative x plus y equals negative 5. The thing to notice is that you have a positive y all by itself. So what I'm going to do, I'm going to solve the top for y. So I need to pick which equation I'm going to start with, and I need to pick which variable I'm going to use. And again, the easiest choice to make this method work nicely is to pick one where, as I put it, the variable is all by its lonesome. The thing about the y in the top equation, it does not have a number in front of it, unlike the bottom equation where you've got 2x and negative 5y. The other thing it has going for it is that it's also a positive y. That's why I chose y instead of the x, because you'll notice the x is negative. Negative x plus y is equal to negative 5. I want to solve that equation for y, which means I'll want to get the y by itself. I will add x to both sides. And when I do that, I will end up with this, y equals x minus 5. What I'm going to do is I'm going to take this thing that I just got and put it into the bottom equation for y. So I've got 2x minus 5y equals 1. That is the bottom equation. What I'm going to do is I'm going to replace y. I'm going to use some parentheses here. And instead of y, I'm going to write this right here, which is x minus 5. When you do this, you're going to want to do the distributive property. The negative is attached right there. So if we do this, this is going to give you 2x minus 5x. Negative times negative is plus 25, and that all equals 1. 2x minus 5x, that is negative 3x, plus 25 equals 1. Subtract 25 here. You get negative 3x equals 1 minus 25 is negative 24. Divide by negative 3. Negative 24 divided by negative 3 is the number positive 8. So I have half of what I'm after. I know the value of x. Now what I need to do is go back and find y. So what I'm going to do is I'm going to take this that I ended up with here, y equals x minus 5. And I'm going to put the value for x that I just obtained into that equation. And so then when I do this, y is going to equal 8 minus 5. 8 minus 5 is the number 3. So we have a value for x, we have a value for y. And then to finish it off, we're going to write our answer like the coordinate of a point. We're going to write it in the form x comma y. So you would write that as 8 comma 3, and that would be the point of intersection. So that is how you can use substitution to solve for a system of equations. So you just pick one of the equations, solve for one of the variables, take the results you get and plug it into the other equation. After you have done that, you'll get a value for one of the variables, put that into the equation you started with, now get you the other value that you're looking for. Now, substitution has its drawbacks because not every equation is going to have a variable by itself, and sometimes solving for the variable can get a little cumbersome. So what you can do as an alternative is use what's called the addition method. So for the addition method, the thing to keep in mind, there's not necessarily like a set way to do it every single time necessarily. But the thing to remember, I like to call this your goal. The thing to remember is your goal, which is you want opposite numbers for one variable. That is your overall goal, to make the addition method work. Now, the thing to notice here, I have a positive x and I have a negative x already in this problem to start with. And if you wanted to, you could write it like 1x and negative 1x if you felt like it. And the important thing, the takeaway from this, is that they already have opposites. They already have opposites. So what that means is you can cut to the chase here. Excuse me. And you can go ahead and add all the terms in the equations from the get-go. So what we're going to do is we're going to add both of the x's together. We're going to add both of the y's together. And we're going to add both of the numbers together. So 1x minus 1x is going to cancel out. 2y plus y is a grand total of 3y. And then -1 plus 3 is going to give you the number 2. You can solve this for y. Y is going to equal 2/3. So we have a value for y. Now we can eliminate again. We're going to repeat by eliminating y. Because by having opposite numbers, that's sort of what you're doing behind the scenes, is you're rigging the equation, you're setting things up so that either the x's will cancel each other out and get eliminated, or the y's will cancel each other out and get eliminated. Now, what is it that you would need to do to try to eliminate something where the numbers don't match from the beginning? Well, what you would do is you would multiply one or both of the equations to get opposite numbers. That's what I mean when I talk about your goal. You want to get opposite numbers for one of the variables. Because the top equation has a +2, what I'm going to do, this y down here has nothing. So I'm going to multiply it by a -2, and a -2 will pair off nicely with the +2 that is already there. So for the first equation that I have x plus 2y equals -1. That one is not changing. What I'm going to do is I'm going to distribute, and I'm going to multiply everything on the bottom by -2. -2x times -x is +2x. -2 times y is -2y. -2 times 3 is -6. Then what we're going to do is we're going to add yet again. And then this time around, we're going to get rid of the y's. The y's will cancel each other out in this instance. X plus 2x is going to give you a grand total of 3x. -1 plus -6 is -7. We're going to divide both sides by 3. And when you do, x is equal to -7/3. And this is also a nice example of what the addition method has going for it. Because, I mean, I can do fractions, but I will be the first one to tell you they're kind of a hassle to deal with. And one of the things that the addition method has going for it is, you notice at no time did I have to mess around with common denominators and all the equivalent fractions and all this stuff. I could just solve the problem, follow the method. If I got a fraction, I got a fraction. You know, it's like whatevs, you know. We can handle fractions around here. No big deal. So this is sort of what the addition method has going for it, because plugging in fractional values can get to be a pain very quickly. Also, this is another problem that shows why graphing has its drawbacks. In case you're wondering, it's like, well, why can't we just graph them all the time? Well, good luck looking at a picture and figuring out precisely -7/3 and 2/3. You know, having the actual number is a lot easier than trying to eyeball it from a picture, especially when you're dealing with fractional values. So here we have another one. They say using the addition method when multiplication is required. So we've kind of seen a little bit of this already here. But what's going on with this one here? We've got 3x plus 5y equals -11. We've got x minus 2y equals 11. And in some cases, you can get away with only multiplying once. A lot of problems, you have to multiply both equations. But here, you can eliminate x And since this is positive 3x, what I would want down here would be a negative 3 to go along with it. Since I've got positive 3 with the x, I want to have a negative 3 for the other x. And if we distribute this here, everybody gets multiplied by negative 3. Let's see what we will obtain. The first equation is not changing. So 3x plus 5y equals negative 11. What do I get if I multiply all that by negative 3? That's going to give me negative 3x. Negative 3 times negative 2 is positive 6y equals negative 3 times 11, which is negative 33. Now we are going to do the addition part, which is where the addition method gets its name. 5y plus 6y is 11y. Negative 11 minus 33 is negative 44. We're going to divide that by 11. And when you do, you get a value for y of negative 4. At this point, you have two options. You could either go back to the beginning and eliminate y, much like I did last time. The other thing you could do, which is in most cases probably the easier way to do it, you notice that this time the value of y I got was just a nice, friendly garden variety negative 4. There's none of this fraction business running around making my life difficult. So what you could do at this point, which is probably easier than going back to the beginning, is you could just pick your favorite equation and you can just plug in for y. Pick your favorite equation. I'm going to pick, I don't know, the top one just because it's first. So if I got 3x plus 5y equals negative 11, we're going to plug in negative 4 right here. And let me just note, you can choose either equation. There's nothing anywhere that says I have to use the top equation. That's what I meant earlier when I said there's not really one set specific way that you can do these problems. You have options. You can eliminate x or you can eliminate y. You can plug into the top or you can plug into the bottom. You know, you got lots of different options here. These are not problems that are nice for indecisive people, because you just have to pick something and commit. There's no wrong answers. You can pick the top, you can pick the bottom, you can pick x, you can pick y. Doesn't matter. You just got to pick something and go with it. It's not for indecisive people like my wife, who has trouble picking restaurants. And, you know, she's like, well, I like Mexican food, but I also like Chinese food. And I'm like, just pick a restaurant, woman. I'm hungry. But so, you know, the joys of indecisive people. So you make a choice and you commit. There's nothing that says I had to put it in the top equation. You could just as easily put it in the bottom one. Doesn't make much difference. So what do we got? We got 3x, and then what is 5 times negative 4? That is the number negative, what is that? Negative 20. And that is equal to negative 11. You would then add 20 since you are subtracting 20. That gives you 3x equals 9. Divide by 3, and you get x is equal to 3. Let's try to do that without drawing through the, there we go. All right, so we have x is 3, y is negative 4. So then when all is said and done, you say, okay, my answer is 3, 4. That would be the point of intersection of the two lines if I took the trouble to graph it, which I'm not. But if you graph them, that would be the point where they meet. And there you go. You have successfully solved a system of equations. Okay, so what else do we have going on here? So here, the name of the example kind of very cleverly points out to us that we're going to need to multiply both times to solve this problem. So before you do anything else, like I was saying earlier, you need to pick which one you're going to get rid of. You can pick X, you can pick Y. Really doesn't matter. There's not a lot riding on this. You just got to make a decision and go with it. I'm going to eliminate X just because it's the one that's first. You could just as easily pick Y, but I'm going to eliminate X is what I'm going to do. So I've got 2X plus 3Y equals -16. That's the first equation. The second equation is 5X minus 10Y equals 30. And basically what we're going to do is we're going to kind of crisscross the numbers here. So you'll notice there's a 5 down here. We're going to put a 5 up here. There's a 2 up here. We're going to put a 2 down there. And when we do that, that'll give us a 10 in both places. 5 times 2X will be 10X. 2 times 5X will also be 10X. Remember what I said at the very beginning, your overarching goal. You want opposite numbers for one variable. That is the goal. We're really close to that because at the moment, I'll have positive 10 for both of my X's. The catch is somebody somewhere needs to be negative. Again, it doesn't make much difference which one I choose to be negative. I can make the top one negative. I can make the bottom one negative. There's not like one set way to do this every single time. That's how it's a little different than a lot of other algebra topics. Somebody somewhere has got to have a negative sign. I'm just going to arbitrarily pick. I'm going to do it on the top. Boom, there it is. Could I have chosen the bottom? Yes. What you don't want to do is you don't want to do both because that's not going to help. But anyway, what we're going to do, everybody's going to get multiplied on the top by -5. So -5 times 2X is -10X. -5 times 3Y is -15Y. And then -5 times 16 is, what is that? Positive 80 is what that is. Okay. Across the bottom, everybody is going to get multiplied by 2. So 2 times 5X is 10X. 2 times -10Y is -20Y. And then 2 times 30 is the number 60. And then now we're going to do the addition here, which is where the addition method gets its name. By design, -10X plus 10X cancels out. That was the whole point of doing this. That's why we did it the way that we did. -15 minus 20 happens to give me -35Y. And then 80 plus 60, what is that? That's 140. And then to finish things off, I'm going to divide by -35. I know 70 divided by 35 is 2, so 140 divided by 35 should be 4. So that should mean that Y equals -4. And there you go. We have found the value for Y. Next, what we then need to do is pick your favorite equation, plug in the value of Y that you just obtained. So I'm going to plug in Y. Again, these are not problems for indecisive people. You can pick the top, you can pick the bottom. Not a lot riding on this choice. Either one is correct. Doesn't really matter. You just got to pick something and go with it. I'm going to pick the top one just because it happens to be first. There's no rule somewhere that says I have to do it that way. It's just that is the choice I am making. I have made my bed, now I will lie in it. I think that's how that goes. Anyway, so what do we have? So you replace the Y with a -4. By the way, please, 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 when you're doing this, if you solve for y and you're going to plug it in, please do make sure you put it in for y. I've graded a lot of math tests over the years, and I see this happen every so often. A student will do the first half of the problem beautifully, and they'll get a wonderful answer for like y. And then they go to plug it in and they put it in for x. And I'm like, oh, bro, oh, y. It's a y. Oh, it's just, you're killing me, Smalls. But anyway, so anyway, if you solve for y, do make sure you put it in for y. I guess that's what I'm trying to get across. If you solve for x, put it in for x. Imagine that. This is why writing down your work and showing your steps and stuff is a good idea. I was not the best math student myself back in the day. I like to show off and do stuff in my head, which was not impressing anybody, because it's amazing how jumbled things can get when you're like 6 steps into a multi-step problem. And it's like my teachers would always just be like, write it down. What's wrong with you? Had it been legal, they probably would have smacked me upside the head. But anyway, let's see. So you've got 2x minus 12. Since you're subtracting 12, you're going to add 12. And when you do that, what is that? 2x equals negative 16 plus 12 is negative 4. Then you divide by 2, and you divide by 2. And that gives you, no, why am I writing y? No, it's x. Almost did it myself. All right. Negative 4 divided by 2 is negative 2. There you go. And so then when all is said and done, the answer that you get is negative 2, negative 4. If you really felt like it and have a lot of free time, what you could do is you could do this problem like in completely the opposite order. You could like solve for x first and then go and plug it in and then like solve for y. And even if you do that in like a totally different order, it's kind of like driving on the roads. There are multiple paths to get to the same destination. As long as you arrive at the destination first safely, that is what is important. So there you go. There is a kind of standard garden variety system with 2 variables and how you would approach it if you're having to multiply both of the equations. Now, I mentioned at the outset that you can also have these things known as inconsistent systems. So let's take a look and see what happens if you have an inconsistent system. Now here, this problem is teed up beautifully to do substitution, because what you will notice is that it has x equals some stuff. So what I'm going to do is, for this example, I'm going to do substitution. This is like the perfect situation that substitution is for, because you've already got x equal to something. So what I'm going to do is I'm going to replace the x in the bottom equation. So I've got x plus 2y equals 13. And what I'm going to do is I'm going to replace the x with 9 minus 2y. And then we will add 2y, and that should equal 13. Now, there's no number I have to multiply here, so the parentheses aren't really doing much for me. So I can basically ignore them, because the parentheses, unless you're having to like do the distributive property, the parentheses aren't doing much here. And isn't this interesting? You've got negative 2y and plus 2y. Those will cancel each other out and give you 0. If that happens, you then end up with a very interesting statement, which is 9 equals 13. Now, last time I checked, that is not a true statement. That is a false statement. False. You rub its nose in it and swat it with a newspaper and say, no, bad dog, bad math. That is not right. It is not true. So, this means that it is inconsistent. That's how, without graphing it, you could tell that it is inconsistent. I'd help if I could spell. It's inconsistent, meaning consistent. meaning it has no solution. So there's no solution. It is inconsistent. And the way you can tell is that you get complete and other nonsense, like claiming 9 equals 13. The other thing that can happen is you can have a dependent system where it turns out that both equations happen to be equal to the same line. So the question is, what would that end up looking like? Well, what we would do first, they say to use the addition method here. So if I've got x plus 3y equals 2, and the other equation is 3x plus 9y equals 6, if my goal is to have opposite numbers, if I've got a 3 down here, what I would do is multiply by -3 up here, because my goal is to eliminate x. That is what I'm going to try to do. So I will multiply by a -3 to make the x go away. If I multiply the top by -3, I will get -3x minus 9y equals -6. Meanwhile, the bottom has not changed. It is 3x plus 9y equals 6. If you then add all of the like terms, that cancels out and that cancels out. Both of them do. -9 plus 9 is going to give you 0. -6 plus 6 is also going to give you 0. And lo and behold, you get the very, it would help if I could spell. You get the very profound mathematical statement that 0 equals 0. I bet you're all glad you're paying good tuition money to take a highfalutin math class to learn such profound truths as the fact that 0 is equal to 0. Who knew? Now, what this means is that this is how you tell without drawing it that this is a dependent system. And again, oh my gosh, I cannot spell to save my life. Dependent. This is a dependent system. Now, how would you write the answer to a dependent system? Well, what you would do is you could say, you could solve for y. You could take the top equation, which is x plus 3y equals 2. You would solve for y by subtracting x. 3y equals -x plus 2. You divide everything by 3, and you would end up with y is -x over 3 plus 2 over 3. And the way you would write your answer is you would say that it is x, comma, -x over 3 plus 2/3. That's kind of the typical way that a dependent system, how the solution is written for a dependent system. You have x and then something for y in terms of x. So that is a dependent system. So depending on if it's true, this, by the way, is an equation of a line right here, -x over 3 plus 2/3. Depending on if it's on that line, it would be a solution. So that's what it looks like when you have a dependent system. And that is the end of section 9.1. So let me stop the recording here for now.